Hello. Now is it audible? Yes, yes. Hmm. So any confusion up to this? So you understand this concept of condensation? So there are two types. Huh. Hmm. So see, if the both the temperature are same, then generally, uh, in a certain case, if you talk about this, just let me move to this slide. Huh. So see, if this is the rod. So if this rod or the plate, if its temperature is 100 degree and the temperature of the vapor is also 100 degree. So at that point, what will happen? So if say these vapor particle both are at 100 degree, then it is in equilibrium. If say the particle of the vapor particle is somehow 90 100.1 degree, so at that cases only condensation will happen. If they are the same temperature, then they are in equilibrium. And also in practice, it is not like that if it is 99 degree, then condensation is happening. At least or 2 degree is required, 2 to 3 degree, most of the surface. So like if I talk about boiling, so what you know when boiling will happen? If the surface temperature is more than 100 degree, that means if the liquid temperature is 100 degree and the surface temperature is 100.1, either boiling will happen. Fundamentally, it is correct, right? Yes, we also know this. But in practice or real life, it is seen that boiling only start if the surface temperature is around 3 degree or 4 degree more than the liquid temperature. Like for water, if the surface temperature is more than 103, then boiling happens. Similar is the case for the condensation. So it may vary from surface to surface. Okay, but at the same temperature, no changes will you will observe no changes. Only you will see the natural convection is happening there. Okay, so up to 100 degree it is the natural convection phenomena, and after 100 degree it is the two-phase convection. Okay, before 100 degree it is single phase. That means only either vapor will only exist or liquid will only exist. But if it is two phase, both liquid and vapor must need to be exist. Condensation, yes, yes. So this concept is for condensation as well as boiling. Both thing will works here. So now if I just show you a small portion of the derivation which is necessary for your exam point of view, that's why I'm showing. Say among these two condensation mode, one is a film condensation, another is a dropwise condensation, right? So among these, which one will give higher, according to you, will give the highest mode of heat transfer? Hmm. Because in the dropwise condensation, the surface is more exposed to the vapor particle, right? Hmm. Say this is a plate, right? So initially, if you talk about if the vapor is formed and there are vapor particle here, so this vapor particle gas comes in contact with this point, this point, this point. Initially, this is I am talking about only film condensation. So this droplet, all these droplet combinedly forms a liquid liquid film, right? So what will happen? Also there is a gravity effect. So after a certain time, it will form this much of uh, this line indicates your vapor layer or the vapor blanketing. So here the temperature of the vapor say TV. So it should be constant, right? Any confusion? Say, I'm just using another color for. Say this is your y-axis. I am just representing the y-axis in this direction, and this is your x-axis. Okay. So if I consider this plate of length L, characteristic length L, right? And for a certain reason, this is your thickness of the, what is this? Thickness of vapor layer or thickness of liquid film. Okay. So as it is a, so that means this is a fully liquid. As the liquid is moving because of the gravity, so its velocity should be very less, right? Very less. But as the liquid is moving, so there should be a hydraulic boundary layer, right or wrong? So the hydraulic boundary layer should be this type. Whatever you have studied, it should be same, right? So the thermal boundary layer concept is hydraulic and thermal boundary concept also develops here. Now, just if I have to find out this value of u means this is u, the velocity of the liquid film in the x direction or the downward direction. So, how you will find out this velocity? So, just tell me which equation is essential to find out this velocity. If you need to find out temperature, which equation is essential? There are three equations, right now. The first is the mass conservation, next is the momentum, third is the energy equation. So, if you need to find out temperature, which equation is essential? Temperature is related to which term? Among these three equation, temperature is related to which term? Which equation? Ayush, temperature is related to energy. And for momentum equation, in momentum, what is there? Velocity is there, na? Velocity and pressure term. So to find out the velocity, what type of equation we need to use? We need to use momentum equation or Navier-Stokes equation. You can say both. So if I apply this NS equation, Navier-Stokes equation, just I am writing in the short form. This is rho capital du. Sorry, capital D means total derivative. I think you forgot this thing. Just I am giving you a recap. Du dt means, now I think you recall this thing. Uh, so this is minus dp dx, it is only for the x direction I am talking about, plus mu. So see here, this change in velocity in the t direction, this terms, what is this? This is the total acceleration term. Already we know that there is no such this term which change, this will be 0, right? So this whole term, because the velocity in the y direction, if I talk about this velocity in the y direction, what is the velocity in the y direction? We need to find out this velocity, but the velocity gradient in the x direction should be, as I have said, that because of this gravity, so the value of u is very less. So its gradient in the x direction is also less. Its variation in the y direction is very less, and in the z direction also very less, right? A term u, if it is very small, say u is 0.5, so the changes of u in the x direction should be much more less. You got my point now. See, initially if it is 0.45, it is 0.5, so the changes is very less, right now with respect to x direction. So this thing I am talking about. Uh, okay, so that's why I am just doing one thing. I am, so this value should be is 0, right? Again, what I have said, that this value, this is quite small compared to this value L, right? So this is in which direction? This is in y direction and this is in x direction. Uh, so if you say derivative in the x direction and derivative in the y direction, which one will be very small? Hmm. So this one is very small. So that means, can I consider this term as 0? Yes, sir. So that means this is 0 and dp dx. So from this equation of Pascal's law, dp dx in the x direction means in this direction, what it would be? It would be minus rho g, right? So what should be the rho? Whether it's the rho of liquid or rho of vapor? Rho of vapor. Okay. Plus mu. Can I write? So see, another thing is there. Here there is another term which is our body force, Fx. So this thing, as there is only y direction, no x, so this partial derivative term I can write in this way, yes or no? In the only derivative form. So that's why I'm writing it here. Plus, what is Fx? It is the body force or the gravitational force. So what is gravitational force? This is rho g, right? So this rho is the rho of okay, water, because the weight is there of the liquid. So I can now, to find out this u, what I need to do? To find out this u, what I need to do? Yeah. So if I integrate it, what I'll get? The first in the first one, I will get mu y plus c1. Next, again I have to integrate. What I'll get? Rho v minus rho l g y square by 2, right? C1 y plus C2. Any confusion up to this? So now tell me what is the boundary condition? For this equation, as how many variables are there? Constant are there? One is C1 and one is C2. So how many boundary condition are required? So what should be the boundary? First boundary condition? Uh, no, u equal to first at x equal to 0, not x, at y equal to 0. This is y na. At y equal to 0, what is the value of u? Y equal to 0 means it is at wall, and in the wall what is there? No slip. That means u should be, your u should be 0. Yes, good. So if you put here, what you will get? This one is 0, this one is 0. So C2 implies C2 is 0. U is 0 na. Next boundary condition is at y equal to delta. Delta means the highest maximum thickness of the fin. So what should be the at that cases what is there? The velocity gradient is should be 0 na. See, the maximum thickness is at this point. What is the value here from the from the hydraulic boundary near? We know this is your initially there is changes with respect to y, but after it is reaching the stable condition, that means there is no velocity gradient. So that so we need to put it here, right? So what should be C1? C1 basically is minus, right? Now I need to put it in this equation. So please remember this equation. I will be writing this on the next page. Okay. So either you need to copy this thing or is it okay? Okay. Please let me know once you write down this thing. So it is okay, I think. Just a minute. Hmm. So your U is, what is U? Rho V minus rho L. Hmm. And C1 is rho V. Hmm. C1 basically is this na, this by mu delta, and Y is there also, right? So if I take some constant here to mu G Y, I can take, so what I'll get there, Y minus 2 delta, right or wrong? So you got, okay. Now one thing I just want to show you one thing. Just see. Now if I have to find out this heat transfer or mass flow rate, say I'm taking a small area here. Okay. So this is your del X, right? This region I'm talking about, this area. Got it? So I am drawing this thing here also. So this is the small area. This is del X. This is at a here from X at this region. So if the mass inlet mass flow rate is, I am using this equation of mass conservation equation. This is the mass flow rate flowing at this. If this is a control volume, right? In the control volume, this mass flow rate is entering, and what is the mass flow rate here? This should be x plus del x, right? And in the control volume, something may be accumulated. So I just write it as m dot c. What is m dot c? M dot c basically is the energy occupied because of this condensation phenomena. Like a vapor particle once coming in contact with the cold surface, it getting converted into liquid. So there is a latent phase change, there is a latent change or the latent heat transfer is there, right? Hmm. So this m dot c basically is your heat absorbed by this liquid film. So what I can write from this one, from the equation of mass conservation equation, whatever be outgoing minus incoming should be equal to, can I write? So now is the first derivative form, this thing can be written in this form, plus d dx of, right? Yes or no? So I can cancel out this one. See, this thing is basically from the first order derivative. This is the formula of the first order derivative, like d dx of f. If you recall this thing, limit x tends to 0, f of x plus del x minus f of x by del x. Got it? Ultimately, what I'll get, this is ddx of m dot x into del x. This is m dot c. What is m dot c? M dot c basically I say that what is the energy input because of the condensation. So if the heat flux because of this condensation is q, and if I divide it by enthalpy, because I know that the heat flux basically is equal to the energy transfer through this enthalpy, right? I know this formula, so that formula comes from here. What is q? Basically this q, if I talk about this q, q is minus ka del t by del y. Here it should be in y direction, right? So the thing is that if you put this thing, if you have this, just see up to this it is important. That thing I have got. Now q, they may give this q. Now if you have to find m dot, what is m dot? How you need to find out mass flow rate? Because I have taken a small area here, right? If throughout the domain I have to take the mass, so what I need to do, I need to integrate it, right? So what should I integrate? I need to integrate what is mass flow rate, rho v, right? Rho va, yes or no? I think you forgot this thing. Not an issue. Density into velocity. This is your mass flow rate rho av na. Ayush, any confusion? Any confusion? If you have any confusion, let me know. So this is the formula. Okay, you just look into this book or previous lecture. This is how you need to find out the mass flow rate. How you find out this mass flow rate? Basically, see, this is a small section, right? In the small section, how you need to find out this mass? Mass, we know that volume into density, right or wrong? So volume basically means density into u into y. U, in the u there is a, this is velocity, velocity into length. So only will get into 1 I can take, because it is a 2D not 3D. So if I multiplied it into 1, then whole this term will count for your volume. Got it? So what you need to do, you need to just put u here, the value of u from this equation you need to put, and after that you need to integrate. So you will get m dot x, and the integration should be from 0 to del. Is it clear? Please let me know. After that I will move to the next concept. Ayush and Ayush or Shashwat? So is it clear? Okay, okay, not an issue. So what I am saying that up to this, I think it is clear, na? So after that, why I am just showing you, you can find out easily. The approach is important. The way you need to find out you, and after that you need m dot x. For m dot x, m is mass flow rate. What is mass flow rate? This is the mass flow rate basically is the mass per unit, not per unit volume. Here it is basically mass per unit time, per unit length. Not per unit length, per unit time. But as it is a 2D, in 2D either volume is there or not, it should be area. So what is mass? Mass means volume into density, right? Mass flow. So rho is density. In place of volume, it should be area. So U is there. U in the U there is a U basically is the rate of change with respect to time, right? And also y is there. So length into length basically is area by time. So this is mass flow rate. So if you integrate this from 0 to delta, so how you integrate? This is constant rho l, and you can get from here, from this you put down this value, and again if you integrate you will get this value of m dot x. Okay. Hmm. And after that, it is quite easy. If you get m dot x, and again you need to integrate and all these things, you will easily get this thing. Okay. So it is not that much required. Up to you, it is important. And after that, please, still you please go through this thing. I'm just showing you this concept. But the rest thing you just derive because from this condensation, but the derivation may come in the exam. Okay. So I am moving to the next concept. This is your boiling. So after before this, I am just giving you 1 minute time to look if you have any confusion up to this. Think and let me know, and else I will start with this boiling. Okay, I am starting this concept of boiling. So what is boiling and in the condensation? What will happen? Basically, here in the condensation, what you see, this vapor is getting converted into liquid, right? And if it comes in contact with a surface whose temperature is below the saturation temperature, right? So in boiling, what will happen? It is a rapid from liquid to vapor. If the heated surface is more than saturation temperature. So my question is that, so what is the basic difference between boiling and evaporation, not condensation? Can you tell? What is the basic difference between boiling and evaporation? Yes, very good. And 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 any other point? Yes, I also can say this thing. Any other? So okay, good. So you've given the first point. You said that temperature, liquid temperature in the boiling should be saturation, right? It should be below. Next is that man-made or a natural phenomenon that is not a it's a no, it's a point, but that not effective point. So next point is that boiling basically is a bulk phenomena. Bulk phenomena means here only it is taking throughout the fluid domain, but in case of evaporation it is a surface phenomena. Only the top surface is taking where. So that is the basic difference. Okay. So see, in the evaporation also, this liquid is getting converted into some vapors. So that means evaporate. In boiling also, boiling is an evaporation process. Someone say either boiling is an evaporation process. Yes, definitely it is an evaporation process. But here this evaporation is a little bit different compared to normal evaporation. How I can say that it is an evaporation? That thing I will discuss in the upcoming slides. Okay. Uh, So, and before this, tell me what are the applications of boiling? Can you know? Tell me some application of boiling. Beside whatever you see in your household you see cooking of rice, boiling of water for bathing, and all these things is common. Like tea preparation, and all these things is boiling phenomena. And apart from this, can you tell me some physical example, the real life scenario example, any example? Very good is used in boiler. So I'm giving you some modern day application. Like, just tell me one thing. Have you ever seen what is there inside a CPU? Normal CPU. So in the CPU there are some circuit, right? So what is there to cool the circuit? A fan is there. Very good. So in CPU there is a fan, and what is the purpose of the fan? Is to cool the circuit, right? This is for our normal computer. So you have heard about supercomputer. So supercomputer is a computer which require which is a computation which have a high computational power. So it can easily like some types of simulation or some types of numerical if you do in your laptop may get slow. But that types of supercomputer is only for those purpose to run appliance to run such application which require high computational power. So there the circuit is quite large. In the supercomputer the circuit is quite large. So for a fan it is not possible to cool the circuit. So what happened? So they just pour the circuit into a liquid. What they did? They just pour the circuit into a liquid. and this liquid is a non-conductive liquid. Why it is a non-conductive? Because if it is a conductive liquid, then the circuit will get damaged. So you have heard about this dielectric fluid. So generally in the supercomputer, the CPU circuit is generally poured in a what I call in a dielectric fluid. Okay. So as this circuit is poured into a dielectric, what will happen? It will transfer the heat to the liquid. No, not that much because you have studied about the natural convection, na? So what happens in the natural convection? The fluid is stagnant, but because of this heating, the circulation, natural circulation is happening. So the fluid is moving in the sense it is because of only natural convection or buoyancy, not by some external force. Okay. So, mm, so these types of here also you will sometimes see that this from this circuit, you see bubbles is coming out. So you see if bubbles is coming out, that means the circuit may be getting heated up, right? So because of this boiling, these types of circuit is getting cool. So hearing this thing because of boiling something is getting cool, it is little bit confusing, right? But this is the phenomenon. Why this thing is happening? I'm just giving you a example. Say the liquid is there, a plate is there. So if the plate is heated, just I'm giving you an example. This is a rod, okay? It is in the liquid domain. So if you applied heat, so what will initially happen? Is the skin visible? So this is the rod. I think my fingers are visible. Uh, So if the rod is getting heated up, initially, say the temperature of the initially the temperature of the liquid is at room temperature. Say today it is 30 degrees. Say so the heater before applying heat, the heater is also at 30 degree, right? So both the liquid and heater is at 30 degree. So as you start to apply heat to this heater, what will happen? The temperature of the heater will increase, but the liquid is at 30 degrees. So what will happen? The surrounding liquid to this heater, this liquid, only the surrounding few liquid of this heater gets heat up. So if something is getting heated up, what will happen? Its density decreases. So if its density decreases, what is its tendency? Its tendency is to rise upward, right or wrong? So it will rises upward as this low density liquid rises upward. The surrounding cold air comes to take these places, right? So this phenomena continues unless and until uh, how long this phenomena will continue? Can you tell? So which temperature? No. If the heater is at 120 degree, so you say that the liquid temperature will move to 120 degree. So up to up until the saturation temperature or boiling point, right? So see. as the liquid reaches the boiling point of saturation temperature, what that indicate? That indicate the liquid has already achieved the maximum temperature or maximum heat. So from this thing, there may be a confusion. Then after that, the liquid will not be able to transfer any heat. So in general thinking, you may think like this way, right? So once it reaches 100 degree, say this is del T, this is Q. I'm just giving you this explanation. Say this heat, you are applying this heat, and this Q is your heat flux. Okay, heat flux basically means heat by area, right? And del T is known as wall superheat. So which is basically surface temperature minus liquid temperature. Is it clear? Huh. So now what I am saying that as this liquid is achieving 100 degree and the heater, see the heater is also at 100 degree. The condition is that the heater is at 100 degree, the liquid is at 100 degree. Okay. So what will happen if you apply heat, more heat? So if you applied more heat, then the temperature of the heater will increase, but the liquid temperature remain constant. So generally what I have said that at this point as the heat temperature of the, what is the definition of boiling? That the if the surface temperature is more than the saturation temperature, right? And before reaching this 100, when the temperature is below 100 degree, what will happen? Natural convection was happening, right? But in practical life, what happened that say at this point, if the surface temperature 104 degree, around 104 degree, if the surface temperature is more than 104 degree, then at that point only boiling starts. Okay. So this region, below this region, it is known as your natural convection. You got it? This is your 0. This is your 4 degree. What is 4 degree? 4 degree del T. Del T basically is the surface temperature minus liquid temperature. If it is 104 degree, what is the liquid temperature? 100. So that's why it is 4 degree. Got it? Huh. So as the surface temperature is more than 4 degree, what will happen? Because I have already said that the liquid is not able to take up more amount of heat because already it's 100 degrees achieved, right? So at that moment, the liquid gets started uh, to convert into vapor from this heated surface. Whatever is the liquid there, this liquid get a little bit superheat. Little bit superheat means 100 degree is the boiling point. At this surface, this temperature is a little bit increased, say 101 degree, and because of this increase, it is getting converted into vapor. Okay. So what basically is vapor? Vapor is also an energy carrier. So the vapor is taking up the heat from whom the vapor is taking up the heat? A rod. So that's why this temperature of the rod is not getting increase up. that much. If the vapor bubbles will not increase, what will happen? It is 100 degree, but the if you are applying heat, the surface temperature will increases on and on, right? Hmm. So at this moment, you will see vapor bubble started to form on the surface. So if you increase the heat flux again, what you will observe? You will observe that the vapor bubble is more in number. So this vapor bubble, the site where this vapor bubble is formed, this is over a surface. Not everywhere the vapor bubbles is formed, right? At a certain position or the certain places, it is getting formed. So this point where the vapor bubbles are forming, this is known as active nucleation site. Got it? This is known as your active nucleation site. So at this point, if the number of active nucleation site is 10, so at this point it would be more than it is 20, then 30, 40, 50, like that increase. So whether that means that if you increase heat flux, increases and increases heat flux, the number of bubbles increases. Uh, Whether that can be possible always, not possible. So after a certain limit, it will get stopped. So up to a certain limit, say this is the maximum point. Okay, this is known as CHF, critical heat flux. You can say this thing. It is the maximum amount of heat. So before this, up to this region, the curve after this, there the curve is also there. So this region is known as nucleate boiling. Why it is known as nucleate boiling? Because and sites are there. So the number of nucleation site increases with heat flux. If you are applying more heat flux, more number of bubbles are forming. Say this region, uh, say initially there is 4 to 5 bubbles, but at this region, what will happen? The number of bubbles is quite large, and if it is quite large, the whole the surface will covered with vapor bubbles, right? So if the whole surface is covered with vapor bubbles, what will happen? The liquid and the whether there is a contact between liquid and the heated surface? No, because the vapor bubble, it's like the film condensation. Okay, so the vapor bubbles in the liquid doesn't comes in contact. So this critical heat flux is the maximum point before after which this phenomena is observed. If the critical heat flux, if after the critical heat flux, if it increases the heat, the surface is fully covered with vapor bubble. Okay, so this is the maximum point. Clear? After which vapor blanketing, you will observe vapor blanketing. And after that, what will happen? Again, a sudden drop you will observe. Why a sudden drop? Huh? Yes, that is an interesting thing. I will explain you. So this is known as this reason. After that, there is a decrement. This is known as your transition boiling. Okay. So here you see once the surface is getting covered up with these vapor bubbles, so what will happen? The heat from the rod will not be able to transfer the heat to the liquid, right or wrong? So what that indicate? That indicate the heat transfer rate. So that's why this decrement is there. Okay. And after that, again you will see a steep increment is there, and it will increases on and on. This is known as your in boiling. Okay. So what is film burning basically? See, this reason, this transition reason generally exists for a very small period, even less than point 30 second. In real life, it is quite tough to get this transition boiling reason. It is a theoretical concept. This transition boiling regime is a theoretical. Up to this, it is a theoretical concept. Okay. So after that, see, as this vapor blanket is, this vapor bubbles is covered with this heated surface. See, before this, tell me one thing. If a vapor is initially vapor is formed here, nucleate here, then it will grow and then it will depart. First, it will nucleate, then it will grow, then it will depart, right? Depart means it will release from the surface. So as this surface is covered with vapor blanket, so this is also vapor bubble. So it will grow and after a few seconds it will getting depart. So at the same moment, what will happen? The bubbles again form, again it will depart. Okay. So the phenomena will be like a column of vapor bubble you will observe, like this type. So and you will hardly see discrete bubbles. You will see line of vapor bubbles, like these types of line you will observe. Okay. So that means the contact of the liquid and the vapor is very far, right? So what will happen as the liquid or the vapor, the heated surface and the liquid doesn't comes in contact, but you are supplying heat. So the heated surface will, its temperature will rise. Yes or no? Rise. So its temperature will suddenly rise, and it will you will see it is getting the red color, like it is reaching this melting point. So I am giving you an example. Say this is a tube, right? So in this point, if you are applying heat, what will initially happen? And this heat, uh, this phenomena is known as conduction. And what happens after conduction? You are applying heat. The surrounding liquid will, surrounding air will heat. And what happen again if you are applying heat and heat? Convection, sir. I am saying that you are applying again heat. So convection, before convection, you are continuously increasing heat. After a certain time, what will happen? That so what will happen if it starts to increase? Hmm. So what that phenomena is known as? So no, forgot about natural. Already natural convection is over. I am talking if you are applying more heat, more and more heat. So after a certain time, you will see the tube is getting the red hot condition. So what happened in the red hot condition? The tube started to radiate. Radiation start. Okay, why radiation start? Because after natural convection, the surrounding liquid is not, surrounding air is not able to take up the heat. At that moment, radiation start. Because in air, boiling is not possible, right now. So similarly here, as this heated surface and the liquid doesn't comes in contact to it, so after a certain moment, this tube is started to radiate heat. And we know that radiation is the highest mode of, so that's why this increment is there. Yes. Okay. So radiation, though, though, though this radiation is not that much here, but still the enhancement is mainly because of this radiation. Okay, and this point is known as your Leidenfrost point. Yes, but see, in supercomputer and all these things, we only deal with nuclear boiling. Even in our institute, in my lab, we are only working up to this nuclear boiling. And heat exchanger and all these things only works on this nuclear boiling. So see, thus as the vapor bubbles are forming, if the vapor bubbles depart from the surface, that means it is taking heat from the tube, right? So it means it will maintain the temperature of the tube or not. So that's why in electronic cooling, if the bubbles are starting to form, that means it helps to cool the circuit. Good. Got it? Hmm. Now, hmm, so you understand how boiling helps in cooling now? Uh, yes, yes. So the thing is that this is a theoretical curve, right? You have talked about this experimental value. Got it? So now I am talking about this curve, how this curve is derived. This curve is basically initially in the starting, and one scientist whose name is Nukiyama. Okay, he is a scientist. He performed experiment using nichrome wire. Nichrome wire. His experimental setup is like this. An wire is there only. A thin wire is there, and he is applying heat. So his experiment is basically power control. Okay. So power control, basically he is controlling the heat flux. What is the input parameter? In the Nukiyama experiment, what is the input parameter? Power control means heat flux control. So what is the output? Temperature difference. So he is not controlling temperature. What he is controlling? He is controlling heat flux. Now see heat transfer coefficient. You have studied about heat transfer coefficient H. H equal to Q by delta T. Remember this thing, not right now it is required. So in the Nukiyama, what he did, he just started the experiment. So initially he started to apply heat flux. Say heat flux increases like this way. Okay. So he will get this curve up to this. Up to this he get this value. And after this what he get? He get this is the maximum point. After this he observed that this wire getting, what do you think? What happens to this wire? No, it is a thin wire na radiation start, because as it is radiation will definitely start, but before radiation the wire getting break up. So say in electric circuit, in a bulb, in a bulb what happens if it is getting overheated? The terminal getting cut out, right? Filament, I am talking not terminal, sorry, it is called filament. The filament getting cut out. So what happened? This wire is getting cut out. So that means after this point his experiment failed. So what he did, he just changed the nichrome wire to platinum wire. Why platinum wire? So the nichrome wire has a melting point of around 1500 degree and platinum wire is around 22 like this maybe. I'm not sure. Check this value. Okay. Say initially this point in up to this initially the temperature of this oil was about 40 to 50 degree maximum 40 to 50 degree, and all of a sudden within a minute its temperature increases to 1500. Why its temperature increases to 1500? Because the oil is getting fully covered with vapor bubbles, and that's why the oil is not able to transfer heat, so its temperature suddenly increases to 1500, and that's why it get melts out and the filament is destroyed. Is it clear? Hmm. Now what he did, he just replaced this nichrome wire with the platinum wire. So while he has done experiment with this nichrome platinum wire, what he observed after this point, uh, the wire will not break up. This filament will not break down. What happens? And after this point, if he increases the heat flux, the temperature all of a sudden increases to this point. Okay, and again it rises upward like this way. So see, in the Nukiyama experiment, after this point, it getting shifted to this area. So the temperature difference, what is the what he has controlled? He has controlled the heat flux, but the temperature difference on the surface temperature he is not controlling. So after the critical heat flux, if he is increasing the heat flux, so that point is shifted to here. Is it clear? That means if it is the if here the temperature drop is 50 degree, here it should be del T is your say 1500 degree, say, or 500 degree, whatever 1500 or C, like this way. This is the del T. Okay. So at that point, the platinum wire is red heated condition and it started to radiate, and because of this radiation, the heat transfer will increase. Is it clear? So it is heat flux, and then the condition is that if you see, then how he will get this region, this transition, and up to this region, how this curve comes. Okay, so for this, what he did, I'm just showing with the red color. For this, what he just started the experiment from the highest heat flux. See, this is the highest heat flux, not highest heat flux. He started from heat flux more than the CHF. Say if the CHF is 1000, he started from 1200 degree, 1200. Okay, is it clear? So he started to reduce the heat flux, and once he started to reduce the heat flux, he is taking the reading of the temperature. While he is taking the reading of the temperature, he observed the temperature reading is like this way. This red line indicates the decrease in the heat flux. So after this point, so on decreasing the heat flux up to a certain point, which is known as the Leidenfrost point, what he observed? He observed that the temperature drop all of a sudden decreases to this point. temperature drop all of a sudden. Is it clear? All of a sudden. And in the above case, what you observe on increasing heat flux, what you observe? Temperature drop increases all of a sudden. So basically the thing is that Nukiyama only get curve up to this region and this region, not this region, transition boiling. So for this transition boiling, what the scientists did, they perform experiment where temperature is controlled, not heat flux. If you control the temperature, only you will get this curve. Is it clear boiling curve? Just tell me one thing. How you can increase the if a surface if you are there is a surface at a given heat flux it will give a definite heat transfer coefficient H, right? So the heat flux is constant. So if I am just giving you a condition that your heat flux is constant, how you will increase H? So for this what you need, huh? You will decrease the wall superheat or temperature decrease. So in the wall superheat, what is constant? Liquid temperature. It is 100 degree na. So only the surface temperature. So you need to reduce the surface temperature. But at a given heat flux, is it possible to reduce the surface temperature? No. So what you need to do? You need to modify the surface, right? So we have studied about enhanced surface, structure surface, extended surface. Remember? So if you use extended surface, then the temperature drops and heat transfer coefficient increase. So you can use coating, you can use this structure surface to enhance the heat transfer coefficient. That's why there is fin, so that the temperature drops is more compared to flat surface. Got it? Any con See, it is not required in your system because the if you are applying a liquid, so every liquid has certain property, right? So if it has certain property, if you are using the circuit at this place, so what will happen? Though it will take up the heat from the circuit, but the optimal performance you will not get. Like for optimum condition, you need to keep it at a certain liquid, and also the liquid that is used, dielectric liquid, is the cost of the dielectric liquid is more. So if you pour your circuit in a dielectric, it costs you around 30 to 40,000 more. So if you can afford, you can use. Okay, so that's why. Even you have heard the word data center. Like most of you are using ChatGPT. So this ChatGPT, the algorithm of the ChatGPT, if you are asking the ChatGPT to prepare a picture or to give you an image, to modify an image, what will happen? It works on some algorithm, and that algorithm has been run by a data center. So there is a lot of energy generated. So for this energy generate, there also data center this uh, dielectric liquid are used, and this phenomena is known as immersion cooling. Remember this one. So in our lab, we are working on this concept. So I think you now you got an idea of the culture of our lab. Okay. So can we move to some numerical question, theoretical question? Just this is some fundamental question you can easily answer. Just tell. The film condensation occurs when the liquid after condensation does not avoid the solid surface. Is it true or false? Yes, because for film condensation the surface need to be fully weighted by liquid. Very good. Can I move to the next one? Hmm. Just check. Huh? Statement? Statement 2 is 2. So option D. Very good. So that's why concept is important. Okay, so I'm moving to the next one. Hmm. So which of the following statement is and or are true? The first is that while analyzing film condensation around a just a minute. While analyzing film condensation around a vertical cylinder, the analysis of the film condensation for vertical plate can be considered, providing the diameter of the cylinder is equal to the film thickness. So we have taken a consider. You remember the film thickness should be less than characteristic or D, whatever say. So which option should be correct? Hmm. Statement A is false. Good. Yeah, statement B is true because the diameter is must be higher than the film thickness. Statement C is also false, so D is also false. Got it? So can I move to the next one? Hmm. Here we go. Hmm. During boiling heat transfer, the bubble nucleation start at the free surface of the liquid. True or false? Free surface means the top surface of the liquid. Huh? Then it is boiling take place on liquid surface or heated surface. So what is it? Free surface of the liquid, not free surface of the heater. So that's why this question is given. It should be false. Got it? So next question. Which of the following is or are wrong? Sorry, I just forgot to mention about this pool boiling and flow boiling. Boiling basically is of two type. One is pool and one is flow. Pool means the liquid is stable. Like if you are heating, in a vessel, if you are heating the water, then it is a pool because the water is stagnant. It is not moving. But if you talk about a flow through a pipe, if the water is flowing through a pipe and you are applying heat, then it is known as flow. Got it? That means it is stable or stagnant liquid. So the first question is that in case of the graph, see, the graph that I have discussed is the boiling graph. This is for pool boiling graph. Okay. Huh. See, the question is that in case of pool boiling, as we increases the temperature difference, first flame boiling starts, which will get converted into nucleate boiling after a certain point. So, in the boiling curve, what thing comes first? Whether flame boiling comes first or nucleate boiling comes first? Huh? See the curve. What first comes the natural convection, then nucleate boiling, then transition boiling, then uh, so the first option is right or wrong? First option, it is false. So that's why it is correct here because the wrong option there are. Next, in case of pool as we increase temperature, first nucleate boiling start, which gets converted into flame boiling after a certain threshold. It is correct. So it is true. That's why it is not the answer here. So latent force point occur before the onset of nuclear. Onset means before the starting. Onset means starting. So either latent force point occurs before nucleate boiling. Do you have the curve with you? Okay, I'm just showing you this curve again. So first, what comes? First comes this latent force point comes after the transition boiling, just before this. Got it? After this class, I will give you this, give you time to draw this one. So this is your false, so it will be the correct answer here, and also it will be false. So A, C, D is the correct answer. Next, I I think that you will definitely answer this one. Hmm. Hmm. That means power control. So it is. Hmm. So temperature he has not control. So answer is good. So this is some of these are some of the question that can be asked from this. And now 2 to 3 questions from the previous class. So for a natural convection around a vertical flat plate, in case of high Prandtl number, the Nusselt number is proportional to the square of Rayleigh number. Is it correct? Nusselt number is equal to C like this one to the power n. I also forgot this formula. Hmm. Yes. Just make mistake. Have I given this concept in the last class? Hmm? Okay. In this, I haven't discussed about Rayleigh number. Okay. Okay. Sorry. So then I just forgot. So there is a correlation between Nusselt number and Rayleigh number. Nusselt number is equal to Rayleigh number to the power n. Okay. So that is a correlation. So this value of n depends on the type of flow. Say n is your one. Just mention this thing 1 by 4 for laminar flow. You know laminar flow and 1 by 3 for turbulent flow. So that means the Nusselt number is not proportional to the Rayleigh number square. It should be proportional to 1 by 3 or 1 by 4. So the correct answer is false. So see again Rayleigh number is proportional to GR into PR. Yes, Grashof number into Prandtl number. So that thing is also there. So this is a concept. So Prandtl number is greater than 1. Okay. Another important thing, always remember this value of n is always less than 1. In majority of the case, it should be less than 1. It can never be greater than 1. Majority of the case. So I'm moving to the next one. Okay. Uh, just check this question. So this question is that which of the following is or correct with respect to natural convection over a vertical flat plate in a low Prandtl number fluid. So Prandtl number can be expressed as a function of ratio of hydraulic, hydrodynamic and thermal boundary layer thickness. Is it correct or not? Definition of Prandtl number is what? Uh, because sorry, Prandtl number is this one. So option one is second option. Just now I have Nusselt number is constant. What do you think? Eh? See, Prandtl number is less than 1. What that indicate? That indicate that hydraulic boundary layer is smaller than thermalic boundary layer. Okay, very less. Just a minute. Let me confirm this thing. Just a minute. I have to recheck this thing one. Hmm. Okay. Sorry. One thing. So the thing is that Nusselt number is not is constant. It can be constant. It cannot be constant. You are right. So this option is also wrong. Okay. So the correct option is option A or B, right? But in the last, according to me, the option should be A and B. But in the NPTEL last year, the answer they have given it only B. So I don't know why. Okay. So, but the correct answer is option A and B, according to me. So, last question for today. Choose the factor for which instability might be created for condensate flow over a flat bed. It is about the condensation. So, among these condition, which condition can causes instability? So, first is the density of liquid, whether it causes instability. What do you think? Density, say if the density is more, that means density is proportional to mass of the droplet or the volume of the so if the density is more, then the volume of the droplet will be more. So definitely condensation will affect or not. So option A will be correct. Next is the surface condition of the plate, whether it will create instability. Say if the surface is rough. So I have talked about hydrophobic, hydrophilic, remember? So if a surface is hydrophobic, the condensation phenomena is one type. If it is hydrophilic, then it is another type. So it depends on the surface condition. Next is the average velocity of the condensate flow. So if the vapor is flowing, say if a vapor is flowing faster rate and another vapor is flowing at a smaller rate, so definitely it will affect because how much it is coming in contact with the heated surface, that is important because we have derived this value of U. You remember? So if this value of U is more, sorry, condensate flow is more, then the liquid film velocity will also be more. So it will be dependent. So option D will be also correct. So all of these four options. So basically that means option D is the, so that's why option D is the correct answer. But in that cases, some people what previously did, they just put all the four answer. So though they have got marks, but it is not fundamentally correct because already all of the above you have chosen, and why need to choose all these three separately? So is it clear? So up to this for today's classes. So any confusion? Hmm. So can we wind up this class? So, uh, okay, okay. Just I'm winding this class, then you can draw this class. Okay. Okay. Thank you. Let me close this.